Thank you very much, and good morning to all. So, this keynote is going to be a bit of a technical talk, and I'm going to try to make it as accessible as possible to a large audience, because I realize that there's a lot of different backgrounds in the audience today. The topic is about new data gathering techniques in wireless sensor networks. This is work that I have done in particular with one of my former PhD students, Madi Nabae, who graduated a year ago now, I think, and is now working with Ericsson. And this is done in the context of the research chair that was mentioned. So this is a research chair that is co-sponsored by an industry sponsor, which is Hydro-Québec, and that's the main utility in the province of Quebec in Canada, where I'm from. And the idea of this research project is to try and see what we can do in wireless sensor networks to gather data from different nodes, measured in different nodes, take them to a sync node, that is the master node that will aggregate all this data, and do that in a way that will be useful to a utility. And so the application that we've envisioned from the get-go is a utility trying to monitor what's happening, for instance, in a power substation. Where they have a lot of different equipment, they could be reading some data from this equipment, and they're trying to gather that data as quickly as possible. And the as quickly as possible comes from the constraint that they have to be able to react fast to any issue they might actually detect with some of the equipment, which some of these issues might actually result in issues in the grid collapsing, blackouts and things like that, but also could result to in destruction of some of their properties, so transformers could explode, etc., if the issues are not detected on time. So the whole idea is the setting of a sensor network, a wireless sensor network, and how can we gather data as fast as we can in order to be able to make decisions. So here's the outline of the presentation today. I'm going to spend quite a bit of time in motivation and background to give you a sense of the existing techniques that are there and why there's something that is missing in the existing techniques. And then I'm going to spend some time with our proposed architecture, which is called here quantized network coding, and I'll explain to you in detail what I mean by that. Thank you, the lights like that is perfect. I'm going to go through possible decoding techniques towards a proof of convergence, simulation results, and also an application in practice, because this is all going to be done at a very high level, scientific, theoretical considerations, and the question is, does this actually work in practice? And I'm going to show you how we actually apply this within a standard compliant framework for our industry partner. So, motivation and background, this is the schematic of my sensor network. So each of these nodes here is a sensor that is wirelessly connected to others. So these are the arrows. This is the way the sensors can communicate with each other. And the idea is that each of them measures some sort of data. And so the classical example that people use all the time is your sensor measures temperature. And what you're trying to acquire is a sense of the distribution of temperature through the space, the field that is covered by this sensor network. And the way you do that is that basically each of these nodes here has a measurement, which I represent by these colored packets here. This represents a packet of data that has to be transmitted to this master node, the red one here. It's called the sync. That's the one that actually is going to gather all the data in one place and be able to have a sense of the temperature field in this example across space. So the idea is that all the nodes have information to communicate to the sync. So each of these blue nodes wants to communicate something to the red node, and this information is typically spatially correlated. The reason for this is that if you look at applications like what was called smart dust at the time, where you would deploy wireless sensor network by just dropping your sensors, it's very clear that most of the times, whatever they measure is going to be reasonably similar to what their neighbors also measure. And so this is going to be an important factor in what we do, is the realization that most often, in most practical cases, the measurements that you have in these different locations, they're somehow correlated. So there's a good chance that whatever this node here has as packet to transmit is close in value to these two neighboring nodes. In order to be able to tackle the problem of data gathering, we make some usual assumptions. So the nodes always have some data, so they measure continuously, and they're always able to send the data. There is some sort of pre-existing synchronization between the nodes. So that means there's really a network that has been established, and so we don't worry too much about having to synchronize these things. And we also use the abstraction that whenever there's several nodes that want to talk to the same node, so we have a way of doing this, and there's many ways of doing this. Could be time division, multiple access, could be frequency division, multiple access, but we sort of assume that we can consider nodes like this that have 2 incoming ports and 1 outgoing port, something like that. For this presentation, the assumptions that are less usual that I'm listing here were for now, for the beginning of the presentation, looking at lossless links. So there's no noise on the transmission. You send something, it arrives on the other side, you're not losing any information. We'll come back to this assumption later when we talk about practical applications. The correlation of data, I mentioned the data that is measured is correlated across space. The way we model that is one specific model, which is the K-sparse or K-compressible model. And let me give you a sense of what I mean by that. If you remember all my data that is measured at any given point in time by my sensor network, if I stack all this data in a vector that I call X, this set of data is called K-sparse. If I can find some sort of matrix that I call phi inverse here, such that the resulting vector, which I call S of t, has a lot of 0 components. And it's called K-sparse if there's at most K non-zero components. That basically means, if you think about it, there's a linear transform that you can effect on your data that makes it look like there's not that much information in that data. So essentially, a K-sparse set of data, like the data that is measured by my sensor network here, only has a very limited number of degrees of freedom. In that particular example here, it's 2 sparse, so that means there's only 2 non-zero components in that transform domain. There's only 2 degrees of freedom that sort of represent the amount of information that is measured by this sensor network. And that represents the correlation. So the fact that the data is correlated is represented by that mixing matrix here. You can also write this equation like this. So the measurements I get from my network, they come from a limited set of degrees of freedom through some sort of matrix that mixes up everything, and that's really what you actually measure. It's the mixed up version here. You look at there are values in every component of this vector, but in reality, behind that, there is a model that has only a very limited number of degrees of freedom. That's a K-sparse system. A K-compressible signal will be basically the same thing, except that instead of having at most K non-zero elements, you have at most K large elements. So you take a tolerance, here I call it epsilon, and you can say that most of the elements in that vector here are small, so in magnitude they're smaller than epsilon, whatever your tolerance here, and the other one are the large ones. So the same idea, there's a limited number of degrees of freedom, and the rest is negligible in terms of the impact it has on the data. And so that's the model we use to say that there's a high correlation between the different measurements in your sensor network. So, with all this in mind, let's look at the existing methods for data gathering. So the most obvious one, the one that is used all the time, is what I call routing and transmission here. So I'm repeating my sensor network here. The idea is that all of these nodes have packets of data they want to transmit, and by default, in routing and transmission, we'll just take these packets and slowly route them through a given path to the sync node, and it would look something like that. So these packets are traveling through your network, they're queued up from time to time at some of the nodes, and at the end of the day, after a while, all the data has been gathered at the sync. That's really the normal way of transferring data through a network. We just use that in a wireless sensor network. So the issues with that kind of a design is that you require some way of routing your packets. So you need to know the layout of your wireless sensor network to define a route between each of the nodes and the sync. That's where your packets are going to travel to. That makes it very difficult to adapt this algorithm to topology changes. And this is something that we also have to take into account when we're doing a wireless sensor network, is that all these nodes in a wireless sensor network have a limited lifetime. And so at some point, they might be running on battery. From time to time, some of them will die. From time to time, you'll have to put new sensors in place. And so it's pretty normal that it would be topology changes. And so if all of a sudden this node here disappears, then all the routing tables have to be redone. That's the network, that's the way networks work. So if you do the classical routing and transmission, you have this issue that topology cannot change too much, otherwise you have to reset and recompute everything. And the other issue you have is that the delay is basically at least the delay is the minimum number of hops between the farthest node to the sync node. So that's the minimum delay you'll have, and that doesn't take into account the delay you have also in queuing. So if I redo this animation, there's queuing at some point here at this node, and so the packets can only leave that node sequentially. So queuing plus number of hops, that gives you the minimum delay you can achieve in gathering the data at the sync node. The final remark about this is that it's blind to correlation. An algorithm like this one doesn't look inside the packets. There is data to be transmitted. It's going to transmit data without taking into account the fact that there actually is a strong correlation between the different packets of data. So one way to take the correlation into account is to do what's called distributed coding. In distributed coding, the network actually has a very fine model of the correlation between the values to be transmitted. And so going back to my example where I was saying, this node here, the value it has to transmit has to be pretty close to the value that its neighbors want to transmit. You can take that into account if you know exactly the model, the statistical model that describes this correlation. You can have this node here transmit the whole information, and this one here only transmit the new information that is different from what this guy is going to transmit. So that this is what I'm showing graphically here by the size of my packets. There is a lot of information in this one. You have to send the whole data, but once you know this data here, this node here needs to transmit a lot less information, because a lot of the information it would transmit is already contained in another packet. The difficulty with this is that you need to know exactly the correlation